So welcome for this lecture, a new chapter and a very interesting chapter at that. It's called the kinetic theory. Earlier we used to call it the kinetic theory of gases, but because the kinetic theory is able to explain many things, therefore we are not confining it to gases, and particularly the rarefied gases, for which the kinetic theory of gases is a likely explanation. The kinetic theory explains the behavior of gases based on the idea that the gas consists of rapidly moving atoms and molecules. This is possible as the interatomic forces, which are short-range forces that are important for solids and gases, which are repulsive as well as attractive, which we use for the explanation of the behavior of solids and liquids. These forces, the interatomic forces, the short-range forces that exist over there to the tune of few Armstrongs to tens, and at times we talk of hundreds of Armstrongs. When I will talk about what is called the mean distance between successive collisions between the molecules, that can be neglected for the case of gases. So it gives us the liberty to get rid of those forces and go ahead. This model, this hypothesis and this explanation, the kinetic theory, is remarkably successful. It gives a molecular interpretation of pressure and temperature. I told you about temperature. I told you that this is manifest in the zeroth law of thermodynamics as an introduction. But the kinetic theory, it gives a better explanation. Of course, there is no clash between the two explanations, and molecular interpretation of pressure and temperature is obtained using the kinetic theory. The kinetic theory is consistent with gas laws like the Boyle's law, the Charles law, and also Avogadro's hypothesis. The concept of a mole, a gram mole, number of molecules or atoms of the gas at STP in 22.4 liters at that set of temperature and pressure is 6.02 into 10 to the power of 23, which is common for all gases. It also correctly explains Cp and Cv, the molar specific heat at constant pressure and molar specific heat at constant power. The kinetic theory relates measurables such as viscosity, conduction and diffusion. Diffusion is always from levels of higher concentration to levels of lower concentration. So relates measurables such as viscosity, conduction, diffusion with molecular parameters, and in doing so it yields estimates of the molecular sizes and molecular masses. Okay, we go on to explain other things. So now let us talk about the molecular nature of matter. Okay, and we'll talk about the atomic hypothesis, which is all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart but repelling, when they are being squeezed into one another, then they repel. And you have seen that repulsion in the case of the contraction of solids in elasticity. Okay. Now, this is the atomic hypothesis. Perpetual motion means the motion is happening all by itself. But there is no concept of perpetual work done. And people are looking for that. They are searching for perpetual work done, which has not been found because of the the first law of thermodynamics, which is nothing but the conservation of energy, and also the other conservation laws. Now, many centuries before Christ, Kannada in India, and a few centuries before Christ, Democritus in Greece, they talked about individual constituents. Anu and Parmanu in the case of Kannada, and atom in the case of, atom means indivisible in Greek language. Okay. So anyway, that was there. So they thought that all things in the Brahmanda, in the cosmos, they are made up of atoms. Okay. Then came in the 19th century the famous chemist John Dalton. He gave the atomic theory, wherein again the same thing, that there are atoms, 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 atoms. So I will just relate to you with one of the things where I was rebuked by one of my teachers. Science tells us, answers us how. Religion may tell us the answer to why. So there was a poem when I was in class 6th, and still my English was very, very poor. So there was a poem. All things bright and beautiful, all creatures big and small, all things great and wonderful, the good God made them all. No problem for me. But there was a problem. There was a big problem to my, when I was a young boy, I asked my teacher, "Sir, I have a question to ask." He said, "Yes." I said, "You said that the good God made them all. Is there a bad God?" And he looked at me, he looked here and there, and then he said, "Sit down." And he never answered my question if gods are good and bad. Okay, because he couldn't understand my question, maybe. My training was that there is only one God, khalas. Okay, for everything. One of my tiny colleagues at that time, after the interval, he took me aside and said, "Yes, there is a bad God, and that bad God is Yamaraj." Okay, no problem. So all things bright and beautiful are creatures big and small, all things great and wonderful, the good God made them all. In those days, there used to be not more than 5 elements, Pancha Tattva. And still, Kannada, in India, long before Democritus, in Greece, he could assume that there is atomic hypothesis. Great people, the rishis of India and the scientists of Greece. Well, John Dalton's atomic theory It explained the laws of definite and multiple proportions when elements combine into compounds. Okay? For example, carbon combines with oxygen to give you carbon dioxide, also carbon monoxide. Hydrogen combines with oxygen to give you water, is H2O. So there are two parts, definite proportions and multiple proportions. For definite proportions, he said that any compound has a fixed proportion by mass of its constituents. For example, in carbon dioxide, we can have 12 parts by mass of carbon and 32 parts by mass of oxygen that will combine together to give us carbon dioxide. So this is the law of definite proportions. The other is that two elements form more than one compound, more, okay, more. Sometimes it happens. Two elements form more than one compound for a fixed mass of one element. For example, 12 grams of carbon. The masses of the other element are in the ratio of small integers. In the carbon monoxide, it's 16 parts of oxygen, and in carbon dioxide, it's 32 parts. So 16 divided by 32 is 1/2, or 32 divided by 16 is equal to 2:1. Okay, so these things could be explained by John Dalton's atomic theory. Very beautiful explanation for the results which were so obvious. Of course, here it's only I've talked about a binary system of compounds where there are two elements. For more than two elements also, when they combine, for example, ammonium chloride, NH and Cl, they combine. Okay, this is not matter. It's for chemistry to explain how to. Well, he also said that atoms of one element are identical. All atoms are identical, but differ from those of the other elements. For example, all atoms of carbon are akin, similar, identical rather, and that of oxygen are identical among themselves, but they differ from the atoms of this. And atoms also form molecules, a small number of atoms. This was thought by Dalton. For example, in the case of rare gases, noble gases, there is only one atom per molecule. But in the case of some of the polymers, the number of atoms can be as large as a few thousand. In the organic compounds, there is a very large chain of atoms, etc. Now this hypothesis says that there is an atom, indivisible, Parmanu, indivisible. But atoms, now as we know, that they constitute of a nucleus and electrons, and the nucleus has got protons and neutrons, and these protons and neutrons, they are made up of quarks. Quarks are made up of something else, but we are not going into those details. In the kinetic theory, it suffices for us, it is sufficient for us to understand that atom is the least and indivisible part of elements. Now the elements are very large in number. Okay, earlier the elements used to be considered in the Greek days and the older days to be only pancha tattva, 5 elements, fire, this, that, I'm not interested. So of the various laws that appeared in the 19th century, there is the Gay-Lussac's law of proportions by volume, which states that when gases combine chemically to yield another gas, their volumes are in the ratios of small integers. Okay. So, for example, hydrogen and oxygen gases, if they combine to form water vapor, then the ratios are in small integers, 2 parts of hydrogen, 2 volumes of that, 1 volume of oxygen will give rise to 1 volume of, etc. Then came a very interesting study which is called Avogadro's hypothesis, which states that equal volumes of all gases at the same temperature and pressure, all gases at the same temperature and pressure, it's not STP or anything like that, have same number of molecules. I told you about that. The number of molecules in 1 mole of each gas at STP, standard temperature and pressure, it is 6.02 into 10 to the power of 23 as calculated in Avogadro's hypothesis, and the volume that it occupies at the STP is equal to 22.4 liters. Now, this hypothesis combined with the Dalton's molecular theory, that explains Gay-Lussac's law. If we go deeper into it, then the atomic size is about 1 angstrom, where 1 angstrom is equal to 10 to the power of minus 10 meters. Often, for larger molecules, the size is 2 angstrom. If we look at, and today we can even look at molecules and atoms, even electrons and other particles with the help of powerful microscopes that we have. So we find that in the case of solids and liquids, mostly, solids are the most ordered system and liquids are less than that. Liquids can flow, solids cannot. Okay, of course there is viscosity in the case of liquids, and that is of the order of 2 angstrom degree. Okay, we write this as angstrom degree. Whereas the interatomic separation in the case of gases, and particularly the gases which are closer to the description of ideal gas, that distance between the adjacent particles, adjacent atoms, the interatomic separation or intermolecular separation in that case is several tens of angstrom. Now they keep on moving. There is a perpetual motion of these atoms, as I told you, and in doing so they can, on the average, the molecules of a gas may travel without colliding with each other an average distance, and that is called the mean free path. These mean free paths are long distances as compared to tens of angstrom. Okay, that all depends upon the temperature and pressure, etc., etc. Now, that gives us a glimpse of, a probe into what is the constituent of the kinetic theory. Okay, these are atoms and molecules, and for a long, many millennia we have had the concept through Canada and Greek scientists, philosophers, that there is something called atom. Atom means not divisible, and something called parmanu, which is a part of anu, etc. in the ancient Indian explanations. So we see that we have laid a foundation of the kinetic theory. I will tell you something more than that. The kinetic theory is very important to us, even in the case of explanation of conduction in the case of metals. There is a free electron theory of metals. So all these things, one more thing I will like to add, that when we are dealing with atoms of the same size and shape and this and that, then we consider, because there are collisions, so for the process of collision, we consider these atoms to be colliding with each other, and they are in the shape of spherical shape, and the collision is perfectly elastic. Why so? Because if the collision is inelastic, then some energy is dissipated in the form of heat, etc. And the perpetual motion cannot be explained. By the way, for perpetual, I would like to tell you, share with you another thing. That suppose I told you about capillarity. In capillarity, if for example the water in a capillary rises, okay, the thinner the capillary, the more the rise. We have learned that. And the shape of the water surface as seen from above is concave. Now suppose I am asking you a question, that in the case of a capillary, the water rises, a particular capillary, the water rises say 15 centimeters. And what if I bring it down, okay, then the water will rise up to the brim of the capillary, okay, and thereafter, do you think that the water is going to fall? Think, and I tell you the result. If the water is going to fall, there is a work done out of nothing, which is the violation of the law of conservation of energy and also the first law of thermodynamics. So what will happen? What should happen? Actually the water will rise up to the brim, and its curvature over here, the curvature that is there, that will start flattening and flattening and flattening until it becomes, if you still lower it, then this will become rather convex. So think about it. The perpetual work done is something which many people are trying to pursue to get Nobel Prize, but I hope that you should not waste your time. I don't think so, to find out any means of perpetual work done. So thank you very much for today, and tomorrow we'll talk about the gases.